Today we have Professor Satya Mandal from University of Kansas in Lawrence, Kansas, and he will speak on Quillen K-Theory, a reclamation in commutative algebra. So Satya, you are welcome to begin your lecture. During the lecture, we will ask you if there are questions from audience. We will ask you to stop and answer them. Otherwise, at the end of the lecture, we will have a free discussion among the audience.
So lecture is for 1 hour till
It's a 1 hour lecture. Yes.
Okay. So I can lecture 1 hour, then you will be asking questions, right?
Yes. Or in between, if some people have questions,
Okay,
we will ask you. Yeah.
Okay.
You may start.
Okay. So thank you for everything. Okay, and this opportunity. You see, when I was a graduate student, we was a graduate student, and Bigal was a graduate student. K-Theory was part of commutative algebra. Okay, and after Quillen published his paper in 1972, he used too much topology, you can say, and too much is a relative thing, okay, and it also depends on how how somebody takes some time to constantly get what is needed. Okay. Now, if somebody tells you that you read the 400-page book of Whitehead and 350-page of Hatcher and two more books, okay, of similar length, essentially 2,000 pages, it's intimidating and it's not doable for most people, we in this present situation, we have to write papers, graduate students have to write papers, okay, and there is limited time. So anyway, so I was always interested in Quillen K-Theory, I mean, I did Quillen module and but anyway, it became not reachable. Okay. So in any case, I worked basically on my, some way or the other, I always had the interest to understand the whole thing. And eventually I managed, okay. So topology that they use is not very deep. It is basically taught to the graduate students depending on what you do. Okay. So I'm changing the page. I hope it changed. Okay. So as the title said, it's a reclamation of K-Theory. So that instructors and the students don't get intimidated, don't feel intimidated. I want to give you some idea what is needed, I mean, in terms of quantity. So in about 120 pages, I consolidated all that is needed. Okay. And all of you, including students, know parts of it. Okay. You and I may not, and two people may not know the same parts, okay? But everybody knows some of it, okay? So I'm saying K-Theory can be taught to algebra students, okay? So after Quillen's paper, what happened to K-Theory? After Quillen's paper, of course, we know what happened from my side, okay? Basically, it is not readable. Okay, some people wrote, Srinivas wrote a book, okay? Eventually, Chuck Bible did a book, okay? And they are really not readable for somebody like me, okay? So what they did is they did what they are good at, that is topology. They built on topology, okay? Did more topology. But original, vision for leaders in algebra was to write this hierarchy into groups in an algebraic way. Okay, not just give a definition. Okay, but in any case, Quillen gave a definition, and it had a lot of topology. It had jargons that most of us were not used to. So what I'm saying that topologists did what they are good at, and algebra community did not provide their input. So there is a gold mine of research potential in algebra. There are two things we can do. One is describe these groups algebraically. Okay, I mean, I'll come to that. And we can also propose some questions in algebra, purely algebraic questions, okay, to simplify and naturalize these groups. Okay, describing these groups are very, I mean, they are at a very, what should I say? I mean, nothing has been done. Of course, we know how to define K1 and K2 of the category of projective models. Okay, but if you move from category of predictive models to category of finitely generated models, okay, then writing down K1 is by itself is difficult. I mean, there is somebody wrote something, and even that is not very well understood. People didn't work on it. Okay, I mean, so even K1 is difficult to describe. Okay, and there are proofs. I mean, Quillen wrote his proof and proofs actually, and I mean, if anything a specialist, somebody like Quillen does, you should be able to simplify. I mean, says conjecture itself. How many proofs in my book? There are 3 proofs. Okay, meaning my book on predictive model. I have 3 books. Okay, I don't know how many proofs Ravi wrote in his book. Okay, so we can simplify. Now I will propose a problem. Okay, so in that regard, so yeah, so I'm going to I wrote 11 chapters. Okay, and I'm essentially going to I will go through these chapters. I mean, what is where. Okay. So chapter 1, so first 4 chapters, is background, that 120 pages I told you about. Okay. In K-theory literature, they put everything in the jargons of categories, arrows. Okay. So highlight of chapter 1 would be proof of a snake lemma for abelian category. It's very interesting. Abelian category, there is this snake lemma, and most of us know its existence. Okay, and this can be taught to the graduate students, but we don't teach. Okay, quotient categories. Okay, I mean, in commutative algebra, when we teach commutative algebra, our limit is inverting a multiplicative set. Yeah, I mean, quotient category and inverting arrows, okay, in a category, they go together, okay. Yeah, I mean, calculus of fractions I wrote here, okay. So we are stuck with teaching how to invert multiplicative sets, okay. And but it takes a little bit. Of course, we have to teach. It's not too difficult to teach people to invert arrows. Okay, I mean, you are probably used to the idea. I mean, Sana gave a talk 2 days ago, 2 weeks ago, and he spoke about quasi isomorphism, which are maps between complexes. Okay. that induce isomorphism, okay, homologies, okay, those things they routinely invert. Okay, I mean basically, you know, you can invert any arrow. Okay, in category of, when you invert the multiplicative set or whatever, okay, if you try to invert 0, okay, then you get something that's not of any use. Okay, I mean, and that it becomes 0, whole thing becomes 0, and that kind of things may happen, but you can basically invert any arrow. Okay. Then, of course, you know, Quillen K-Theory, basically, even I would say, even before Quillen, exact categories where, I mean, we knew, you know, exact category, for exact category, we can define K naught. Okay. I mean, when I was younger, I gave talks, you know, saying that, you know, think of any category where I didn't know the expression exact category. So I said, you can think of any category where exact sequences make sense, then you can define K naught. Okay, so that is a serious definition, and so that is included in chapter 1. So I would say most algebraists know this part, but not necessarily very algebraists, meaning both faculty and students, okay, know this part, but not comfortable enough to work with it. Okay, so that's not me. Okay, second chapter is Homotropic theory. Okay, we'll see that for an exact category, A group Ki of E is some homotropic group of a topological space. Okay. Um, in K-theory literature, they use both homotopy and homology. You know, I mean, of course, homotopy and homology interact. You know, you can derive information from each other, and those things are used. But I avoided homology. So in about 20 pages, I wrote down what is needed. I mean, this chapter will have 40 pages roughly. In about 20 pages, I wrote down what you need to know about homotropic theory. It's interesting that homotropic theory is not taught in the first course in algebraic topology. It is in the second course. Okay, but you need about 20 pages to, yeah, I mean, to know it. Okay. Then I discussed quasi vibration in another 20 pages. It's told some theory that is not really, I mean, that's not so basic. Okay. So let me say some of the things about topology, homotopy theory. Okay. First, start with algebra. Okay. See, if we have an exact sequence of complexes of modules, you can write down a long exact sequence. Okay. I mean, Amyo Mukherjee taught me this when I was in ISI. We can, yeah, I mean, if we have an exact category, we can write down a long exact sequence. But actually, we can do better. If I give you just one map of the complexes M to N, then you can write down the cone. Okay, Cn of f is n of n direct sum m n minus 1. And with this cone, you have a triangle. Okay, so so basically you can write a map to from n to c the cone. You can write a map from n the complex n to the complex cone. Okay, and they fit in a triangle. You can write down a long exact sequence. That's all I'm saying. Okay, and that is my, so what I'm saying is, given any f, it fits into a long, I mean, it fits into a triangle, and you can write down a long exact sequence. You know, I mean, I wrote down parenthetically, and that was the birth of triangulated category. Okay, triangulated category, what they do is they just formalize this. Okay, whatever happens with such this to the whatever properties of complexes of modules that somehow, yeah, I mean, with this, they just formalize and write down a definition of triangulated category. Anyway, so that was algebra, okay? We are all used to this. And thing is that these things, I mean, I would say, did not come from, actually came from topology. I mean, I would say topology is mother of pure mathematics, okay? Algebraic topology, okay? Lot of things, even category theory, I mean, I would say comes from topology, okay? So I want to do reverse engineering since we know algebra, okay? So given a continuous map of pointed spaces, we can write down a topological space which I denoted by f of f. F is the map, uppercase f of lowercase f. I also wrote down the base point. So what is that? That is all pairs x comma gamma. X comes from, first coordinate comes from x, and second coordinate is a path in y starting from fx going to the base point b0. Okay, and if you have this, you can write down long exact sequence of these three things, you know. I mean, I have three things, you know, the homotopy fiber f comma b0, I have x and I have b. Okay, you can write down a long exact sequence. Okay, I would say idea of cone came from this. Okay, so this is slightly generalized. You know, if you have any map from f to x comma 0 to b comma 0, then if something is, if f is homotropic to this homotopy fiber, then I call this sequence on the top a homotopy vibration. You know, there's a natural map. When you have a map from f to x, you have a natural map from f to this homotopy fiber. You send x to x comma the constant path at in b, of course. Okay, so yeah, fx will be b naught, okay, for all x, and you will send it to constant path x. So if this is a homotopy equivalence, of course you can replace the homotopy groups and they will be, so you have a long exact sequence, okay. So you would have a long exact sequence, okay. Just replacing the homotopy groups of this by homotopy group of f, okay. So quasi vibration, this is not so basic, you know. I mean, homotopy theory has a base point issue, and if f is a map from x to b, and for all b, you can look at the fiber, fb equal to f inverse b, and we say f is a quasi vibration if fb, the fiber to x comma x to bb is a homotopy vibration. Okay, consequently, for each fiber you have a long exact sequence. Okay, so anyway, that's Dole's thumb, and its characterization of quasi vibrations is important. You know, Quillen K-Theory, you will see in theorem A and B, there are two theorems called theorem A and B. And many people wrote many versions of theorem A and B also. Okay, and these are basically, if you would like, you know, fork and knife of the dinner. Okay, these two theorems. Okay, so anyway, that goes into quasi vibrations. Okay, so I had to do this in 20 pages. Okay, chapter 3. Chapter 3 is CW complexes. Okay, CW complexes, CW complexes has a very rich and accessible theory. Okay, Hatcher's book is the main source. Okay, so what you do is, you have, so X is actually is a CW complex. It comes with a sequence of subspaces x0, x1, x2, and union is xn. So this can be an infinite sequence of subspaces. Xn is called n skeleton. X0 has discrete topology. Now you build xn from xn minus 1 by attaching open disk. They're called cells, n cells, open disk of dimension n, of course, to the skeleton. Okay, so I mean, I like to put things in category theoretical languages, and so you have a push forward map. Okay, so xn minus from xn minus 1, you're trying to build xn. So you have a family of cells, n cells. Okay, it's they are where the rim of dn, meaning that disk that you are trying to attach to xn minus 1. So the rim is, of course, the image of Sn minus 1. So Sn minus 1, so there is a map from Sn minus 1 to Xn minus 1. This is given map. Okay, so and so this is a push forward. So that's in the algebraic language and geometric language. I'm still more comfortable with algebraic way of looking at things, formal way of looking at things. So this is a push forward diagram in the category of topological spaces. Okay, so you are attaching cells. Okay, so so again, I wrote 20 pages on this. That's all you need. Okay. It's a very nice theory, I mean, CW complexes, as you saw, it's built from disk and sphere. By sphere, I mean the hollow sphere, okay, and the disk, the total disk and its boundary, okay. That's how. So it enjoys a lot of properties that dn comma Sn minus 1, Sn minus 1, dn comma Sn minus 1. Enjoys. One of them is homotropic extension property. Okay, and okay, so it's very interesting theory, and I want to say one. I mean, given a map from continuous map from x to y, a weak equivalence. Yeah, it's called weak equivalence if it induces isomorphism of homotropic groups. Okay, weak equivalence is a very broad, as I said, everything may have come from topology. Idea of weak equivalence may have come from topology, but weak equivalences are defined in any homotropic category. In many categories. Okay, quasi isomorphisms you are familiar with. Okay, a map between two complexes of modules is called quasi isomorphism if they induce isomorphism of homology groups. Okay, and they are, they form they are weak equivalence in that category. What do you do with weak equivalence? You try to invert them. Okay, so I think Sarang Sar mentioned weak equivalence in his talk. Okay. Most frequently used result and very important an interesting result. If you have a map of two CW complexes, not just topological spaces, CW complexes, F is a homotopy equivalence if and only if F is a weak equivalence. So to check something is homotopy equivalence, you just have to check that map of homotopy groups are equivalent, are isomorphisms. Okay, that's all. Of course, you have pi 0 also. That also you have to say that they are isomorphic. Okay, induced map is isomorphism. Okay, and this is very widely used theorem because you can apply in many cases. Okay, in our context. And there's also other theorems. I would like to focus on the first one, meaning not say emphasize the second one. Basically, you have the skeletons, okay, of a CW complex. So homotopy groups are determined by skeletons of homotopy groups of the skeletons. Okay, so let me not re-emphasize. Anyway, talk will be available. It will be available from my site also. Okay, so I'm moving to chapter 4. That's chapter on background. Okay, simplicial sets. In CW complexes, what happened was that skeleton was there, then you attached cells. Okay, and cells were attached along the rim. Okay, along the rim, and those maps are given maps. Somehow you knew those maps. Okay, CW complexes are basically breaks down that information in basically combinatorially or set theoretically. Basically, in CW complexes, you start with points, okay, then you have the lines, then you have the triangles, okay. Here, these lines, these points, the edges, the triangles, they are given as sets, okay, and there are maps, okay. So in CW complexes, you will attach the maps by a given continuous map. And here, once you have these points, lines, triangles, etc., okay, how to attach them to, these rims, let's say, how to glue this rim to the previous skeleton, that is kind of given. There is not much flexibility. It comes algebraically, more or less, okay. So anyway, so to define that, I have, we call that delta category. These objects are, I wrote in bracket, that is just the set 0, 1 to n. And from M to n, maps are all non-decreasing maps, okay? Non-decreasing map, okay? And there are, special arrows, they essentially generate all these maps. That is phase, I wrote them phase di from n-1 to n, and degeneracies n to n-1. So what would be di? Di is you just skip one, okay? Yeah, you skip I, okay? Okay, and degeneracy you just merge two of them, two consecutive. You just put them together. So they actually, these maps in this category are compositions of these maps, okay? And so anyway, I look at E0, E1, E2 in R infinity, okay, basis, okay. So these are sequences you can call, okay. Now you can define sigma n to be T0, T1, Tn. This is the standard n simplex. So summation Ti is 1 and Ti are between 0 and 1. Okay. So of course we all know this. Okay. This is called standard n simplex. I still did not define simplicial set. Okay. So this is a covariant functor from the delta category to the category of topological spaces. I mean, this is topological spaces, but this is restricted to much nicer to category of topological spaces. Okay, now simplicial set. Simplicial set is a contravariant functor. I denoted it by K bullet, okay, and K bullet is so I mean K0 you should think of points, K1 are the edges, K2 are the triangles, and so on. Okay, I see I messed up a little bit. The geometric realization. Geometric realization is, I mean, you cannot see it. I mean, somehow I didn't pay attention. Okay, so you look at. So say sigma n is in Kn. Okay, that's n simplex. Okay, that's the n simplex. Okay, so that should be treated as that sigma n, other sigma n I wrote down. Okay, this standard n simplex. So you take, we will write it as sigma cross this sigma n. Okay, this sigma n. So you take the disjoint union, and you along this maps, it's a contravariant functor. Okay, this is a contravariant functor. That's a covariant functor. You can use them to identify points with n the lines and lines with edges of the triangle and so on. Okay, so this is hidden. Okay, so simplicial set has a nice geometric realization. Okay, and main thing we need to know is that this geometric realization is a CW complex. Okay, it's a CW complex. So you can use everything you know about CW complex. I mean, that's a very rich theory. As I said, Whitehead's theorem, I said, if it is if the map is weak equivalence, it's homotropic equivalence. I mean, so, and I mean, so this is another 20 pages. So this is all the background you need. Okay. So that's all we need. Now let's get into Quillen's paper. Okay. Classifying spaces. We will be, of course, we want to compute the define and compute K groups of a exact category. So this is a step before that. Okay, I just told you what a CW complex is. The NURB of C is defined. So NURB of C will be a, NURB of C will be a simplicial set. I just told you what is simplicial set. Okay, so what is an n simplex sigma? It's a sequence of composable arrows. You start from x0, go up to xn. Okay? Okay. Now, it is a functor from delta category. So how do you define the maps sigma n to, meaning n to n, sorry, n n of C to nm of C. This is obtained by inserting identity or taking composition of successive arrows. Okay, so these are non-decreasing functions. So some of them will repeat, and some of them will be dropped. If it is dropped, you compose the arrows. Okay, some integers will be dropped, and some integers will be repeated. Okay, so if it is repeated, you put an identity. If it is dropped, you compose. Okay, so I gave you given a category, I gave you a simplicial set. It has a geometric realization. Okay, it has a geometric realization. Okay, and that is called the classifying space. Okay, BC, I denote it by BC. This is called the classifying space of C. Now, what you do with them, immediately you define the homotropic group. Pi n of C comma x is defined to be, so x is an object in the category, pi n of BC comma x. Okay, yes, that's good. And good. Okay, so let me quickly tell you. So goal will be to, given an exact category, somehow define pi n of that category, meaning k n of that category, as some homotropic group of some topological space, which will come essentially this way, comma 0. Okay, so that's the goal. Okay, so anyway, quickly, so this comes from these are geometric realization of simplicial sets. Okay, now you take, given a covariant function, it induces a map of the classifying space. Very simple. Okay, I mean what can you do? Okay, so we get a continuous map. So B, that classifying space, is actually a so I denote this category CAT cat. That is the category of all small categories, and its maps are functors. So B is actually a map from this cat to the category of topological spaces. Okay, so C goes to BC and F goes to BF. Okay. I believe I am still doing very simple things. Okay, that is easily teachable to the commutative algebra students. Okay, only thing I believe was slightly difficult was what I told you about quasi vibrations. Okay, that 20 pages, we need some work. Okay, and some instructor will probably just state the theorem, and probably, we do that, all that kind of things. Okay, good. So that's the functor. What else we know about functors? There are natural transformations. I give you two functors from C to D. There are natural transformations. Okay, if theta is a natural transformation, that induces a homotopy from BF to BG. Okay, they're not very difficult to prove, but even if they are difficult, let's say difficult, somebody has, they're fairly simple. I shouldn't say difficult, but they are very easy to believe actually. How this abstract idea translated to homotopy, that's very interesting to me. Okay, just a natural transformation leads to homotopy of the corresponding maps. Okay, not only that, if you have two functors in the opposite direction, and if they are adjoint to each other, then actually they are homotopy equivalents. These maps are homotopy equivalents. Okay, and consequently, if C has an initial or a final object, then it is contractible. It's contractible, so it has no homotropic groups, 0. Okay, so we will be working with exact categories. So if we just look at B of C, we will get nothing. We'll need some work to do. Okay, so that's classifying spaces. Okay, yeah. So the plan is to given a functor. So I told you about the homotopy, meaning homotopy fibers and the long exact sequence of homotopy groups. That is something I'm trying to implement in this context. So what is a fiber given a functor f from C to D? What is a fiber? F inverse y is x in C, so that fx equal to y. So then we have a sequence of functors, categories, f inverse y to C to D, and we would like to, we cannot do it, okay, we would like to write a long exact sequence. I mean, in topology also, I give you a map and you look at the fiber, you cannot write down a long exact sequence. Okay, that essentially has to be quasi vibration. And when do you want to use it? You know that if I give you a scheme and a closed subset and corresponding open subset, you would like to write down long exact sequence of K groups. Okay, so that's where we would like to implement. So I'm giving you some prelude what we are going to. It's very interesting. I mean, schemes. We talk about schemes. Okay, but if I'm confined to affine schemes, this doesn't work very well. Only open set that is still affine is if you invert just one element. Okay, so there is not much you can do with that. Okay, fine. So as I said, I cannot do that always. Okay, so I'm defining this given a functor f from C to D. I define y slash f. Okay, its objects are x comma u. Okay, so y comes from D. Okay, x comma u. Such that u is a map from an arrow in D from y to fx. And morphisms are, you have y to fx1 u1 and y to fx2 u2. Then morphisms will be a morphism from x1 to x2, so that this diagram, by writing f okay, this diagram commutes. Okay, if you think about it, it is exact analogous to homotopy fiber. What was homotopy fiber? It was x comma a path from fx to the base point. Okay, so here base point, you should be thinking of base point as y. So I'm looking at x comma u is an arrow which represents a line or a path. Yeah, it's a line in the, if you want to think of in the geometric realization of the nerve, it's a line. Okay, so that is precisely what it is. Okay, so this is analogous. Okay, okay, but so this is how I define this. Okay, fine. So I can also define f slash y by reversing this arrow, so which is dual formulation, just making a point. And if I give you an arrow from y to z in D, then let me call them homotopy fiber. Okay, I shouldn't actually. So z slash f to y slash f, there is a this V induces a functor. Okay, so sending x comma u to x comma uv. Okay, and that's very nice actually. That's very nice because topology we cannot do. Topology, there is no natural map from one fiber to another, or one homotopy fiber to another, unless there is a path connecting those two endpoints. Okay, but of course I said this is nice, but here also I'm assuming there is an arrow from Y to Z. Okay, so they have to assume there is a path. Okay, so anyway, here is theorem A. If given a functor from C to D, you assume that Y slash F, this homotopy fiber-like things are contractible. Then F is a homotopy equivalence. By the way, I mean, you translate borrowed jargons from topology directly to category theory. When I say F is a homotopy equivalence, I mean the map of the classifying spaces is a homotopy equivalence. Okay, so as always, there will be a dual formulation of this by replacing Y slash F to F slash Y. Okay, so this is theorem A. I told you theorem A and B are the knife and fork of the dinner. Okay, theorem B. So now I have a functor. F is a functor. Then I told you this V star. If you have an arrow, okay, from Y to Z, I think okay, then V star is a functor. Okay, you assume these functors are homotopy equivalences. Okay, these functors are homotopy equivalences. In that case, this diagram, given any y, so I'm assuming this condition for all arrows. So Y slash F to C to D, and this is Y slash identity D. This is a homotopy Cartesian. But anyway, I mean, I didn't define what is homotopy Cartesian. And anyway, still, I mean, this has an initial object. So this is the homotopy. This is just null homotopic. Okay. So in any case, you know, I mean, what it boils down for us is that it leads to a long integral. So this upper Y slash F to C to D, this is a homotopic vibration, meaning, you know, this leads to a long integral sequence. You know, we would be seeking for long integral sequence of K groups. So this is what we will be using. Okay, so condition was that fibers are the fiber-like things. Okay, they didn't give a name to that. Okay, these fiber-like things are homotopy equivalents. They are homotopically equivalent, meaning their classifying spaces are homotopically equivalent. So I told you classifying spaces. Okay, first 4 chapters I gave you the background, then I gave you the I said about classifying spaces, and I told you if I give you an exact category, it has an initial object 0. Okay, then it will its classifying space will be trivial, so we don't get anything out of it. So we have to do some work. So Quillen defined a new category given E, an exact category Q of E. Okay, its objects are same as the objects of E. Okay, and a morphism from X to Y, two objects, is essentially, this kind of pairs P comma I, where I is a basically an injection, okay, and injective map, and P is a surjective map, okay. So I mean, this is X. So there are three things: Z, P, and I. Okay. So for we are working with exact category, so we'll have to be not known things. It's abstract, so we have to be careful. So what is I? I is a injective map, which is also called inflation. Okay. So meaning there is an exact sequence from Z to Y to C. Okay, this is an exact sequence. Likewise, P also fits into an exact sequence. Okay, that is K to Z to X. If I give you an arrow of projective models P, surjective arrow of K will be, you have a K, but if I give you injective map of a projective model Z to Y, co-kernel will not necessarily be a projective model. Okay, so we are requiring that will be a projective model. Okay, so then we have a arrow. Okay, I mean these are equivalence classes. So two things are identified if you can join them by a isomorphism. Okay, so a morphism is an equivalence relation. Okay, it's not very equivalence class. Okay, I mean it's not very different. I mean, as I said, this tau is uniquely determined. There is no choice here. Okay, so although I'm calling it equivalent classes, I mean K-theory, they sometimes get into set theory related issues, so they have to say all these things. Okay, I mean when we define K-theory of projective models, we also identify isomorphic projective models. So those kind of things you have to do. Okay, good. I mean, you would like to know what is the composition. So if I have an arrow from X to Y like this, I have an arrow from Y to Z. I take the pullback of W and V. Okay. Now I have U to X is surjective map, and U to Z an injective map. Okay, so this will be the composition of these two arrows. Okay, X to Y to Z. Okay, so good. So if I was talking about projective models, what is it? So I am trying to define a map from a projective model X to Y. Okay, so my Z is actually X direct sum K. Okay, and my Y is X direct sum K, that was Z direct sum, it's co-kernel. Okay, so if you're thinking of a projective model, this is what we are doing. Okay, and thing is that, yeah, if you're working with modules, then it is we have more flexibility. Okay, I mean there's no functor from E to QE. This category is denoted by QE. But if I give you an inflation, meaning an injective map, if you're thinking of projective model, it's a split morphism. Okay, split inclusion. Okay, then I can associate an arrow in Q category. So basically, I'm taking identity from X to X. Okay, and same iota from X to Y. If P is a deflation, we can similarly associate an arrow in Q category, that is P is the same surjective map, and from Y to Y I take identity. So this is good to know. Very good. Let's come to our business. Okay. So suppose E is a exact category. So I know we all know how to define K0. K1 is a different issue, but K0 we know how to define. Okay. I denoted it, this classical K0, I denoted it with a C, with an apology, I would say, because Ki should be what we always known. But in this context, I started using Ki for Quillen K-Theory. I reserve that. So there is a map from, I still didn't define hierarchy groups, okay? So there is a map from K0C, the same old K group, Wilson-Dick group, to pi U1, not pi 0, pi U1 BC, classifying space of the Quillen category, comma 0. Okay. Okay. So there is an isomorphism. It needs a proof. It's not very difficult, but I will give you the map. Okay. So K0C of E is defined by isomorphism classes of objects or predictive models, if you like. Okay. Now there are two arrows in Q category from 0 to X. So one is, I just said, 0 can be, from 0 to X there is a injective map. We use that to get an arrow from 0 to X there. And I also have identity from X to X. Okay, I use that, and I have a epimorphism from X to 0. So I have two arrows. Okay, and two arrows will give you two paths. Okay, two paths. I denote them by from 0 to X. I denote them by gamma 0 X and gamma 1 X. Okay, so if you combine them, you get a loop at 0. Okay, by reversing one of them. Okay, so our map is just sending X to this loop, and then of course you have to check that this is well defined and everything, and then prove it is isomorphism. So I gave you that map. I mean, so I think I have 1 minute. I will finish in 1 minute. So suppose E is an exact category. It's easy to see that pi 0 is of the classifying space BQ E is 0, because 0, I mean, it's a connected space, okay, because 0 is there. There is always an arrow. I just showed there is always more than one arrow from 0 to any X. And from that, you can see that it's a connected space. So it is 0, pi 0. And Kn of E is defined to be pi n minus 1. So our classical 0 was pi 1. So Kn I define as pi n plus 1. Okay. And there is something called loop space of a topological space at a point. You take all the loops at that point. So that homotropic groups of the loop space differ by homotropic groups of the original space by degree 1. Okay. So if you have loop space, so that we call K-theory space. Kn of E is equal to pi n of Ke. Okay. So that works out. Okay. Meaning, so this and this will differ by 1. Okay. Degree 1. Classically we had three groups. I'll stop soon in a few seconds. So it has three groups. These people prove that these are this coincide with Quillen K-Theory. I did prove K1C of R is K1 of the projective modules of R. Okay. for any commutative ring, all credit I'm trying to take here is that I simplified the proof. Okay, I simplified the proof. Okay, and I will come to that. Okay, and I think that will be a good point to stop. So I define Quillen K-Theory, K groups. Okay, I define the classifying space, and I also define the so-called K-Theory space. I will tell you that they are basically same information, and I made considerable amount of progress. Okay, so I mean, what is coming is, now I did basically background. I did background. You know what theorems to expect. If you have any familiarity with K-theory, you know what theorems to expect. Okay, those familiar theorems, expected theorems are coming. Okay, then what we have to do? We have to prove. I just stated that K1 agrees with the K1 I knew. Okay, and so that's another chapter. I will work on that. I'll just state it. I already stated, and from then what comes after that? K-theory of schemes. K-theory, they do whatever they do. They don't do anything that's not homotopically equivalent. Meaning, Kn of AT has to be equal to Kn of A in some way. Okay. So they would always like to have it, otherwise they will stop working with them. So that K-theory of schemes, K-theory of schemes, and my book ends with Swan's paper on K-theory of quadratic. That's the most beautiful application of Quillen K-theory. Thank you for today. Okay, so.
Thank you, Satya, for your very nice talk. We are now open for discussion. Any questions?
Sharing? Shall I stop sharing?
Yeah, we invite people for any questions and comments.
Okay, Dipendra came. Okay.
Yeah, any questions?
Ravi, I didn't tell you your problem, so that will happen next time. Hope you come and you solve the problem.
Yeah.
Ravi, you are here?
Ravi is here, but let me ask you a question as an outsider.
Yes.
So I want to know whether there is a problem about polynomial ring over a field, which this theory about higher K groups is needed to solve.
There are some results on fields. I think it is finite field. I'll check what is there. There's some results in fields for fields. One of the main criticism of K-theory, and they also say it, that is there is not much that has been computed. Higher K groups have not been computed. And that is something commutative algebras can take interest and do. At least for K1 of category of finitely generated modules, there is a theorem, but that has not been dissected enough. Okay. Yes.
Okay.
So Satya, which theorem were you talking about?
What's
of
the
mine?
question? No, I was not talking about your theorem. I was talking about, I will give you a problem, and that I didn't state today. And you come on
which problem?
Huh?
Which problem?
Oh, okay. I'll give you a version of Quillen.
Because Quillen is all smooth, right?
I'll give you a version of Bus-Quillen conjecture. You'll have to prove it.
Oh, I see. Okay. Yeah, it's all smooth levels.
Huh?
Yeah. Everything is smooth in Quillen.
Everything is smooth. It doesn't have to be, not everything is smooth. That's not correct. Okay.
Okay.
That's not correct. I mean, there's a huge theory of theory um, on schemes. Okay, and those things work fairly well actually. But if you want K-theory of projective models, those things do not work that well. So basically, there are theorems for schemes, okay, and then in the regular case they coincide, okay. So that's all they have, okay. So projective models things do not work that well. I mean, what can work, there is a theorem called divisage, okay. Basically, if you have a ring, I mean, k groups of predictive models, not predictive models, the finally generated models should coincide with the k groups of the reduced ring.
Right.
Okay, that you do not even have for k1, right? You just take a look at it. Okay. So, I mean, there is problem for that, but they have worked on it. I mean, and I am just working on Quillen's paper, but Quillen's paper was written in 70s. So how many years? It's about 50 years. Okay, and a lot of work has been done. Other people have done other work. I mean, worth mentioning is Waldhuizen. Okay. So, I mean, those things apply to K-theory or, for example, category of complexes, finite complexes. Okay. So those things work. Okay. And I mean, what doesn't work? Of course, doesn't work. I mean, K1 of predictive models is not same as, yeah, I mean, that research doesn't work, I mean, you cannot do anything about it. Okay, so what can you do? Okay, so, I mean, a lot of things can be
worked out, yes.
simplified. I mean, today I have 22, I hope I will have 12 on Friday.
Mm-hmm. Very good, very good.
Okay, good
Okay.
talking to you.
Are there any other questions?
So, Amartya, you are here, are you listening?
Yeah.
Who?
Yeah.
Amartya,
Amartya has some
Amartya.
questions.
are you there?
Yes, yes.
Amartya is left?
Okay, Amartya, I'll tell you, I was able to do this because I had an education in ISI. I mean, Ashok Mitra, B.V. Rao taught me topology. Okay, I mean, I am talking about point set topology. Okay, and Amiya Mukherjee taught me algebraic topology. Okay, that education was very helpful. I mean, subsequently I did things in Tata Institute. I learned other things in Tata Institute also, topology inclusive equation. But but anyway, point I'm trying to make is that the dose of topology that I got in ISI, I hope that has not disappeared. Okay, I hope you are teaching topology in the same way I was taught. Okay.
I have tried my best to retain point set topology.
What?
See, this point set topology,
Yes.
it tends to get undermined.
Yeah, and that's a mistake. People who do not
Yes,
know, I mean, the whole thing is category theory. I told you that all the functors goes from this to the category of topological spaces, and then you have to, since everything has to work work category theoretically, they have to refine those the right hand side category of topological spaces. They have to think about compactly generated category of compactly generated spaces and such things. I mean, all this I said about CW complexes. Product doesn't work too well in category. Product of CW complexes do not work too well in the category of topological spaces. Okay, so you have to think about more basic things. And it's very interesting. If you look at some of the things, I mean, the papers of Milner on all this topological thing that has been used, they use basic, I mean, if it is separable space, I mean, if you look at Swan's theorem on correspondence between projective models and projective models and vector bundles, I mean, he said, if the space is paracompact, and if the student doesn't know what is paracompact, okay, and never heard of it, then you're lost. So yeah, I mean, a lot of people do not understand importance of general topology. Okay.
Yeah, I tried my best to retain as much as possible when this our master's math program was being formulated. And in addition, I advise students that whatever is taught, it's okay, but on your own, you should read general topology
Right.
from the
So,
classical books.
So Kaushik says Bourbaki 10 chapters.
Bourbaki?
10 chapters.
10 chapters. Okay.
He has written in the chat.
Okay. Thank you.
Okay, so we'll meet on for the second talk on Friday, but we have